Hello and welcome to lesson 5.4, differentiation rules for exponential functions. So today what we're going to do is we're going to take those exponential functions that we just learned how to find the derivatives of and mix them with other functions. So let's start it with this first one. We're going to find the derivative of this function y equals e to the exponent 2x minus 7. Well, if we remember from yesterday, the derivative of such exponential functions are themselves the same exponential function times the derivative of the exponent, which in this case is 2. And if you need to, you can also multiply by the natural logarithm of whatever the base is, but in this case it's because the base is e, the natural logarithm of e turns out to be 1. So you don't need to write that. Again, most commonly, we write this expression so that you put the constant in front, and you get this as your derivative. So let's try the next one. Well, this kind of function, notice that you have x cubed times 3x. Sorry, 3 to the exponent of x. Because these two are multiplied, you're going to have to use a product rule. So first work out the derivative of the first function, which is 3x squared, still multiplied by 3 to the exponent of x. Then you add, this time we leave the x cubed alone, and we multiply by the derivative of 3 to the x. Well, the derivative of 3 to the x is 3 to the x times the natural logarithm of 3. Now, most commonly, what you want to do is you probably want to place this in factored form so that you can find maximums or minimums from this. So, try to factor this. So the common factors here are x squared and 3 to the exponent of x. This leaves me with a 3 in the first term plus an x natural logarithm of 3 in the last term. And there we go. There's our derivative. Again, you can rearrange this in any kind of form that you prefer. This time I've placed the constant ln 3 after the x so it doesn't confuse by putting the x with the 3. Okay, so let's try this next one. This next one, again, notice you've got a product of two functions. So you're going to have to use this product rule. So the derivative of 3x squared is 6x. Leave the e to the negative x alone. This time leave the 3x squared alone. And find the derivative of e to the negative x, which is e to the negative x times negative 1. If you want, you can simplify this first, make your life a little bit easier. And then after that, you can try common factoring. So common factors here are 3, an x, and an e to the negative x. So it's going to leave me with a 2 minus an x. And there we go, there's our derivative. Okay, so again, this one is a product of functions. I'm going to have to use product rule again. Derivative of 5 to the 2x is 5 to the 2x times the natural logarithm of 5 times 2, because that's the derivative of the exponent. Still got to multiply by sine 2x there. Now add. This time I leave 5 to the 2x alone. And derivative of sine 2x is cosine 2x times 2, because again, got to work out the derivative of inside the function. Well, again, you could simplify here, but I'm going to try factoring first. The only thing that I can see that's common is this value of 2 and this 5 to the 2x. So that leaves me with ln 5 from the first term and sine 2x. And from the second term, just cosine 2x. And there we go. There's our derivative. Okay, so as these derivatives are a little bit more complex, just make sure you're keeping up and showing all your steps. Okay, so let's start out with this one. Let's suppose f of x is equal to x times e to the negative 2x. This might also be written in another form. This could have been written as x over e to the 2x. So you could have used product rule, or you could use quotient rule, whichever form that you would have preferred to actually calculate this derivative with. Now I prefer product rule myself, so derivative of x is 1. Leave the e to the negative 2x alone. Add. Leave the x alone now, and derivative of e to the negative 2x. I've got to multiply by derivative of the exponent, which is negative 2. Okay, try common factoring again. And there we go. There's our derivative. Now, because our next question is looking at specifically the equation of the tangent line when x equals 1, you don't necessarily have to simplify this or factor it. You could have probably left it in the previous form and would have worked out just as well. But let's go with what we have. So to find the equation of the tangent, I first need to substitute 1 in for the derivative. Let's see what I get. That's going to give me e to the, my apologies, I forgot to substitute the 1 in the exponent. So this gives me e to the negative 2, or if you wish, 1 over e squared. I also need to see what it is if I substitute a 1 into the original function. So if I substitute it into the original function, I get 1 times e to the negative 2, which is also 1 over e squared. So the slope and the point at the spot is the exact same thing. So now I'm going to substitute that into the format y equals mx plus b. I know what y is. It's 1 over e squared. Slope is also 1 over e squared. X is 1. So I can figure out what b is. In this case, the value of b is just 0. So that means my function for the equation of this tangent is y equals 1 over e squared times x. Or e to the negative 2 times x. Either option would work. Okay. Using example 2, determine intervals of increase and decrease, as well as intervals of concavity for this function. Ooh, okay, so we're going to use our derivative that we see right here. I'm going to write that right here. Just going to refer back to it. There we go. Okay. So, find out intervals of concavity for this item. That requires a little bit more process. Okay. So first of all, set this equal to 0. Well, first of all, an exponential function can never equal 0. So the only time this could ever equal 0 is if 1 minus 2x equals 0. So that means x could only equal a half. Okay, Well, I'm going to create an interval chart to look at x values less than a half and x values greater than a half for this function. So I'll be able to find my intervals of increase and decrease. So again, substitute a value less than a half into your expression. Let's say 0. If you substitute it back into your derivative, you're going to get that value as a positive value, so that means it's going to be increasing. And if you substitute a value, let's say bigger than a half, let's say 1, you're going to get a negative value, therefore your function's decreasing. So let's put that, therefore f of x is increasing on the interval from x greater than a half and decreasing on x greater than a half. Okay, so, well, in order to find our intervals of concavity, let's find our second derivative. So our second derivative, using the first derivative, derivative of e to the negative 2x is e to the negative 2x times negative 2. Leave the 1 minus 2x alone, plus leave the e to the negative 2x alone. Now derivative of 1 minus 2x is negative 2. Again, common factor out that. Both have a... I'm actually going to common factor out the negative 2 here and the e to the negative 2x. That leaves me with a 1 minus 2x plus 1. Now we want to find when this is equal to 0. So 1 plus 1 is 2. Okay, so this will equal 0. Again, this part can never equal 0, so this will only equal 0 when 2 minus 2x is equal to 0, or x equals 1. Okay, so let's create another interval chart. Look at our second derivative. I'll tell us what f of x is doing on either side of x less than 1 and x greater than 1. Okay, so choose a value less than 1, let's say 0, substitute it into our derivative. That's going to give us a negative, meaning it's concave down. Choose a value greater than 1. That's going to give us a positive value. So that's going to give us something that's concave up. So that means our function, f of x, is concave up on x values greater than 1, and concave down on x values less than 1. And there we go. Now, the next set of parts of this lesson is optional for you to listen to or attend to. If you don't want to continue with this, you may exit right now. Okay, so here's an extension of this, and this means that you won't actually be tested on this in this course at all, but I thought it'd be helpful to know how to do this. So first of all, what we're going to do is we're going to actually find the derivative of ln x. And to do that, what we realize is the inverse of ln x, y equals ln x, is actually written as x equals e to the y. So what we're going to do is we're going to find the derivative with respect to x of both sides of this expression. Well, the derivative of x is just 1. The derivative of e to the y, however, is something different that we've never actually seen before. Notice that this variable is a y instead of an x. But we do know how to find derivatives of exponential functions. They're themselves exponential functions, the same exponential function, times the derivative of whatever the exponent was. So the derivative of the exponent was actually y. Well, what you'll notice is on this side, you get a dy over dx by itself, or if you wish, call it y prime. So you can solve for dy over dx just by dividing both sides by e to the y. Well, if we go back to our original expression, e to the y is actually just the variable x. So dy over dx turns out to be 1 over x. And therefore, we found the derivative of our function, ln x, in terms of x. Now, please realize, because e to the y is always greater than 0, sometimes what they'll do is they'll put absolute value signs on this value of x just to show that it's always going to be a positive value and never ever changing. Okay? So, what you can do now is, now using chain rule, you can actually find the derivative of every natural logarithm function. So if you have f of x equal to ln of h of x, then the derivative is f prime of x is 1 over h of x times h prime of x. Well, with our previous work, this piece looks like that constant that we found when we were looking at the derivative of exponential functions. So it looks like that constant that we saw before, which is very, very interesting. Okay, so let's differentiate this logarithmic function right here. So I'll find the derivative of this thing. This is 1 over 2x cubed times the derivative of 2x cubed, which turns out to be 6x squared. Well, what you can do is you can now cancel some stuff. So 2 goes into 6 3 times. Because there's 2 x's in the numerator and 3 x's in the denominator, you can cancel 2 of them here, with 2 of them there, and you're left with 1 in the denominator. And there's our derivative of this function. So now you know how to find derivatives of logarithmic functions. Now you can also find derivatives of base logarithmic functions like log to the base 2, log to the base 3, of other bases other than the natural exponential function, just by doing log base change formulas. Okay? And thus concludes this lesson.